aromatic compounds are not as reactive as one might be led to believe by the presence of alkenes. This is because aromatic compounds are much more stable than non-aromatic alkenes. Because of this, we cannot use the reactions of alkenes as a guidepost for the reactions of aromatic compounds. They have to be taken as two separate things, and quite often they are not at all related in any way. In this reaction, we have an electrophilic substitution. It is a two-step reaction, and it begins with an electrophilic addition. This electrophile needs to be something very strong, like a halogen cation. When we have our strong electrophile, it will react with one of the carbons along the ring. When this takes place, it will interrupt the aromatic effect of the compound, because when it bonds to one of the carbons, that carbon will no longer be sp2 hybridized. This carbon has 1, 2, 3, 4 bonds. It is now sp3 hybridized. Since this is sp3 hybridized, we cannot have that ring of p orbitals that grant that aromatic effect and increased stability. At the same time, because this has taken one of the bonds that was previously a double bond here, we now have a carbocation, and this carbocation is delocalized along the remaining sp2 hybridized carbons. The second step involves a base, and the base will come and remove the proton, which is bonded to the carbon of the electrophile. And the result is a substitution, electrophilic substitution. The electrophile has been substituted for the hydrogen. A very simple reaction on paper. One important question to consider is, why does this base not react with the carbocation? Because carbocations are very reactive. And to understand why this does not occur very often, we have to think of the energetics. We'll use benzene as the example. Recalling the energy diagram of the different number of pi bonds in a six-member ring. Recalling the system of two, whether they're conjugated or not, a six-member ring with 2 pi bonds compared to the energy level of a six-member ring with 3 pi bonds, benzene. Benzene is actually lower in energy than either of the 2-member rings, the 2 double bond rings, whether they're conjugated or not. So to break the first bond of benzene is an endothermic reaction. This electrophilic addition is an endothermic reaction because the increased stability of the aromatic nature of the compound is broken. So it increases the energy level. When it removes this proton, that effect resumes. So now that increased stability is back. And what will happen is that although this first step is an endothermic reaction, the second step is an exothermic reaction. So normally what will happen in an exothermic reaction is the first step is endothermic, and then this is very exothermic, so the total is an exothermic reaction. The total is negative still. It's a loss of energy. Whereas if this base were to add on the carbocation, it would still be at a very high energy level, would not get an opportunity to release energy. So energetically, this is more reactive than the carbocation because it allows for the sp2 hybridization and delocalization of electrons to occur again.